Good evening, the class. Great pleasure to be back and continue the journey on chain conformation. So for today's lecture, we're going to go through two additional components. First, as you will see today, we're going to discuss about what is a statistical chain segment. Then we will go into a little bit more details, talk about chain rigidity, and specifically understand the concept of cone length, persistence length, as well as the concept of wormlike chain model. Why we need to worry about rigidity and chain conformation as long as we already have discussed all the parameters we talked in the past related to different chain model. A quick recap what we have discussed. First, we have talked about how does different chain conformation using free joint chain model, free rotation chain model, hinder rotation chain model. I hope by now you should be able to understand how does different bond angle and dihedral angle would apply to those chain models. We also discussed how does these different chain model would impact the end-to-end distance. As we have discussed in the previous few lectures, the expansion of the chain coil are due to the limits of the bond. So if you have, for example, free rotation chain model compared to free joint chain model, you would have expansion factor would be equal to 1 plus cosine theta divided by 1 minus cosine theta, where the cosine theta is the bond angle, okay? But the end-to-end distance is not a good parameter to talk about the rigidity of the chain. Why is that the case? Because the molecular weight has a huge impact on different bond. For example, if you have a large bond versus a large molecular weight as a small molecular weight, your end-to-end distance will change. I can make a polystyrene end-to-end distance anywhere from 1 nanometer to 100 nanometer by changing the molecular weight. As you see, it's proportional to degree of polymerization power of 0.5. So that is not a good parameter to tell you how rigid my polymers are. But what we're going to talk about today is another parameter called, what we're going to call it is persistence length. This is a more reliable and accurate way to determine end-to-end distance. But before we start that, I'm going to first discuss with you about what is statistical segment. I think we passed that, but we didn't talk in a lot of detail. So let's first start from there. Okay, here you go. So everybody should be able to see the screen quite clear. So again, this is a lecture about chain flexibility and how we can use a very important parameter to discuss what the chain flexibility. So we will talk about how does we determine a flexible chain as shown here, where you can see the chain can be bent very easily to something like semi-flexible, where there's some bending and torsion along the backbone, but it will appear more rigid than the first one. And last one, where we're going to talk about a rigid chain, which means the chain is very much like a rigid rod, so that it doesn't behave like something like flexible coil. And we show two arrows. One is end-to-end distance, the other is sort of local direction of the chain conformation. And as you can see, they would impact how your chain conformation looks like. So as we go back to what we have discussed, the end-to-end distance can be decomposed into a self-turn and a cross-turn, right? We discussed the difference between these two. A self-turn is basically talks about how does the vectors multiply to itself and how we can achieve self-turn end-to-end distance equals to n squared and plus a cross-turn. And I have already introduced in the beginning of this lecture, end-to-end distance actually is not a good parameter that you should focus on when you discuss the rigidity of the polymer chain. We want something more deeper, more insightful, and more interesting. So that comes down to this slides. We need to finish about what is a statistical segment. So this is related to one of the homework you has been asked, especially the homework one. We talked about chain statistics in regards that we asked you about what is the statistical segment first means, and how can we conceptualize it. So let's start with the first part. So as we mentioned, if you have bond angle is fixed, which is a more realistic model, but this would introduce more complexity in your data interpretation as well as finalize your results, because free joint chain is the most simple model, and we know that we can even eliminate the characteristic ratio term C infinity before NL square, so which is very ideal. And in this case, this would be the free joint chain, and this is going to be free rotation chain and the hindered rotation chain model. For those two, they will both show a C infinity term, and that's something some of the theorists want to eliminate even that, because we want simple math, we want simple equation. So a concept they give, so now listen carefully, a concept they give is, can we put a black sheet on our molecular cover here? Okay, I cover this molecular so you don't see anything inside. Only thing we know is end-to-end distance is from here to there. End-to-end distance is what you can see, but anything in the middle you can't see. And you also know that number of repeating unit is n. So the question some of the polymer physicists ask is, can we convert a free joint chain, a free rotation chain to a free joint chain model? Which means we don't want those limits in the bond angle. This turned out to be possible, and it's not complicated at all. The only limitation we ask is put on dark cross so we don't anything inside. So that means your end-to-end distance will be equals to C infinity NL squared, as I show in here, what we know in the free rotation chain model. But in the free joint chain model, if we can visualize them, we can draw number of M bonds, but now the bond length will be different. It can be slightly longer than a single bond, but if we have this bond length, if NB squared would be equal to end-to-end distance, which means it will be a free joint chain, then we can describe the same length scale for the molecular as well. So two models describe the same length scale, and this is called statistical chain segment. And statistical specific means it's something not real, but it's there for you to use it. Okay, in other words, you can consider this end-to-end distance either these free joint chain model shows in black lines where you have bond angle limitation and this showed up C infinity, or you can simply use MBL square. And in the textbook, if you go to the table, we actually listed a lot of common polymers, persistence lengths, as well as statistical segment lengths in there. And the value is typically on the order of few angstroms up to few nanometers, depending on how rigid your polymer chains are. So in other words, how do you calculate it? Very simple, statistical. For given polymer, using the measurement we did in the, for example, in GPC or any other light scattering technique, you can get end-to-end distance R squared. Number of repeating unit, please be careful. This n and this capitalized n are different. The definition of the first m is the definition of the number of bonds along the backbone. And L is a bond length. So you can think about n as how number of these black segments along the backbone. You can count. This is probably 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So each one of 7 bonds, so you can multiply by 7. So there's a total of 49 N or bond. represented by a single segment here, a short carbon-carbon black dot line. Here, N means repeating units. So repeating units means how many repeating units along your polymer backbone. Using the polyethylene as an example, repeating unit N would be equals to number of degree of polymerization. And bond will be twice of number of degree of polymerization. So mindful of the difference. And you know the N, so you can, you know the R, you know the N, you can calculate out what the B is. Okay? We additionally, we can get this statistical segment, as I mentioned, is basically some sort of equivalent to a free joint chain model, give you the same end-to-end distance as shown here in the table, in the illustration here. We can envision that the black line would be a free joint chain, a free rotation chain model, while the red line would be a free joint chain model. Okay? And there are some links between different models. So in the first case, we can see here, I already explained what M and L is. Be careful that NL is different in a sense that this is a bond, number of bonds, okay? And L is bond length. So if we take it as NL effective is basically, we can think about this would be related to MB squared. This is statistical segment length, and would be number of bonds along the backbone. So using this equation, you can already see how we can calculate out about number of cone segments per chain, as well as number of cone segments. And cone segment is nothing fancy but a term defined as we show here. Cone segment is equal to C infinity L divided by sine theta divided by 2. Okay? Yeah, and cone segment again is very similar to the statistical segment we have talked about in the last. The reason people want to come up with complicated term is so they can use a very simple free joint chain model to describe a lot of findings they have in their theory model. So conceptually, you should know what these means if you heard about this, these different models. And we already talked about statistical segment model, which is B, and N is, I explained this would be number of bonds along the backbone. Okay, so one of the good things is, as you can see, the statistical segment's length will not depend on molecular weight. It doesn't like end-to-end distance where you can compare. It will go up with degree of polymerization. If you have higher degree of polymerization, your R end-to-end distance or R square will increase. But the B, the statistical segment length, will not increase because the molecular weight has already been encoded in this value of N, also known as degree of polymerization. Okay, that's very good. A lot of time you will encounter in the measurement of your polymer, you will come up with a term that is related to show here. And what's unique about this is where you can use a simple end-to-end distance divided by molecular weight. In the monomer molecular weight, you can get this relationship. And this relationship can easily use to calculate the equation shows above about statistical segment. As long as you know what would be the monomer structure or molecular weight for the monomer, okay? If you know the chemical structure, you can add all the atomic numbers to calculate our monomer. Like polyethylene, we did in a quiz in the class, you know that the molecular weight would be equals to 28. So now coming back to persistence length, I want to use more physical meanings and terms to help everybody to understand. There is a physical meaning which is defined by this, and I'll explain the equation. So this L is the bond length. So it's a bond length for a single bonds, and this L1 is a vector for the first bond angle. Okay, so that's the first bond in a given chain. So if I'm going to draw, this will be 4 segments of different bond. This will be L1 vector. Second bond will be L2, and we have L4 vector. And R is the end-to-end distance, which is defined by a sum of all the bond vectors. So if you add L1, L2, L3, L4, you would be ending up with end-to-end vector, which is R. And if you use this equation, which shows what's the projection of your end-to-end distance along the initial bond direction, would it be defined as persistence length. And the physical meaning is very easy to understand. I want to use a garden hose to explain to you. So the persistence length of the garden hose is somewhere over on the 1 feet or something like that. And a simple way to visualize and understand the persistence length is through the use of the degree of rotation for the bond along its initial direction. So let me see if I can find a cable in my room and I'll explain. So here is one. So if I use this as an example, what you would see would be there is initial direction where this connector is going, will be pointing up, right? And as this walks around the chain, the direction changes from up to the right and to the downward direction. As you can see the shape of the my tool, right? So the definition of persistence length is very simple, is where you can envision that how long it takes a chain to bend about 90 degrees. So it's when the chain orientation, which is pointing up to the right hand by 90 degrees, the distance that it has traveled is roughly the persistence length. So in other words, in this case, we know that persistence length would be equal to how much? Roughly, I showed in that tool is about, I would call it maybe 3-4 centimeters long. For a garden hose, if I use this piece as an example, originally it was going this way, pointing this direction, and it was slowly bending this way until it's going that. So how long it takes to bend from 90 degrees to this way, to roughly here? So the distance from here to here is something we call persistence length of the polymer chain. So how long it will be going in one direction. So as you can see, if we have really rigid rod-like polymer showing here, then it will never bend more than 90 degrees. So your bond or persistence length will be infinity long, and it will be larger than the contour length. This could happen in some of the polymer that your bond length is longer, your contour length is, your persistence length is equal or larger than contour length. Okay? So coming back to the garden hose, the contour lens is so useful in the sense that it's very direct in the visual parameter for you to envision how flexible the chain is. So let me give you 2-3 examples. So if I have the polymer chain behave like this garden hose, if I'm looking at the scale of length is much smaller than persistence. Remember I said the length for the persistence length for the garden hose is about 1 feet. So if I talk about in a length scale about 1 centimeter, which is much shorter than 1 feet, it behaves like a rigid rod. So if I just cut a local region of the hose, it behaves like a rigid rod. On the other extreme, if we think about if I have 50 feet long hose, maybe the case here, our hose will behave like a flexible chain, right? Hose will bend and go anywhere it's want. It's basically like a flexible chain. So persistence length will give you a reference number for you to judge if the polymer will behave rod-like or flexible, and compare, do apple-to-apple comparison between different polymer chains. You can compare polystyrene with PDMS. Polystyrene has a persistence length. It's shown in the textbook. I don't remember the exact number in my head, but it's about 0.8 or something like that. which is higher than polyethylene or PDMS. You could also compare other more rigid polymer, like our group research on a class of polymer called semiconducting polymer. They're made of aromatic backbone and make them more rigid. So their rigidity is typical 20 times than polystyrene. Other example that people always talk about is DNA molecular. Those are the molecular made up in our body, and they are very rigid as well. Their rigidity can be up to, persistence length can be up to 200 nanometer, which is hundreds of times higher than polystyrene. Quite amazing how rigid these are. Okay, so those are the fundamental concepts about persistence length, and I speak about several persistence length with regular polymer. What you have to learn is what is definition of persistence length, and how do we get persistence length with various measurements that we can do inside a laboratory. Okay? All right, next, let's go through a little bit of math. So this is a definition about persistence length. And as you can see, if we are a free rotation chain, free joint chain, what I'm trying to make, free joint chain means there's no bond limitation. So the average of this term would cancel out for L1, L2. We know that free joint chain, this will be equals to 0 and all the rest of the term. So for free joint chain, the persistence length will be equals to L1 dot L1, which will be L squared. As I already mentioned, L is a bond length. So L squared divided L will be equals to L. So in other words, for free joint chain, the persistence length will be one bond. The second bond will be already had the ability to bend by 90 degrees, which is exceeded the definition of persistence length. Okay? And for free rotation chain, it will be a little bit more complicated. I discussed it in last class lecture. It's involved quite some math into it. If you are interested and want to go deeper in the math, you can either reach out me to schedule a time or watch the video where we have discussed in 2019 class. Okay, so this is what I mean by if we consider not free joint chain, but something a little bit more complicated. So each definition means what's the projection of second bond on the first bond length. So if we draw 3 bonds, L1, L2, L3. So L2 dot L1 means how much component has L2 in the projection of L1 direction. This will be equals to L2 cosine theta, right? And you would also have projection of third one would be equals to L. You need to consider 2 projections on projection to the L1. L3 projection to L1 will be equal to first projection in the L2 direction, then L2 projection to L1 direction. Okay? So there's multiple projection happening, and you lose the amount of directionality, as you can see, the more you bend. In this case, L1 dot L3 will be equals to L squared cosine theta 1, theta 2. Theta 1, theta 2 is defined as bond angle between different bonds. So L1 and L2 bond is defined with theta 1. L2, L3 bond, this one is defined as L2. Okay, so we can get, what we can get here is basically now L1, Lij dot will give you what we call it for a fixed bond angle. If your bond angle is fixed, then you can calculate any bonds along the polymer chain, any I and J bonds, so you don't know where they are. They can be generalized equals to L squared cosine theta absolute of I minus J. If they're next to each other, you can apply to 2 minus 1, then this will be translated to what we have shown above. Okay? In other words, this is quite useful in a sense, help to understand using the concept of projection, using the next bond, projecting the previous bond to help you understand how much persistence length would be for a given bond angle. So it's actually also quite easy to understand in the concept that the flexibility is related to this concept of persistence length and characteristic ratio. We discussed the characteristic ratio. We also call it expansion factor when you consider different bonds. If you have a bond that is more rigid, then your chain would expand more, right? So C infinity is, we call it expansion factor. When you add a fixture in the bond angle, your chain can be expanded 2 times, 3 times, as we show in the previous work. So turns out to be this persistence length is related. How they are related, it can be reflected in this simple equation where your LP would be equals to what we show here is characteristic ratio divided by 2 multiplied by the bond length. So if you know the characteristic ratio or rigidity of your chain, you can translate into persistence length. And translation is very simple. You just divide it by characteristic ratio by 2, then multiply by L. And the other term people also use is to define a term called a Coulomb length. Coulomb length is defined as twice of the persistence length, so quite simple. As showing here, Coulomb length will be twice of 2LP. And the Coulomb length then can be simply understood as a way for the chain to bend about 180 degrees, because persistence length is bending 90, and Coulomb length will be turned back to the original direction and bend 180 degrees. Okay? So this pretty much summarizes what we want to discuss about this very useful and important term of persistence length, LP, and how does it relate to the characteristic ratio, as we talked about in the last few lectures. What is more interesting and more useful is to get a more generalized model for polymer. As we have discussed a lot of time in the previous lecture that free joint chain, free rotation chain have some limitation. What's the limitation is you always need to have flexible bonds along the polymer backbone. If you have something like rigid backbone or fused rings, like benzene ring or fused polymer ring, like my field deals with conjugate polymer, so you have a lot of aromatic rings, ester rings around the backbone, then the bond, if you have a double bond, then it doesn't rotate for that 2 carbon. It's just a fixed there. So we need to use slightly different term. And the term people talk about is called a wormlike chain model. Wormlike basically says it's more rigid than flexible. Worm is something semi-flexible. Okay, I like the term of semi-flexible than wormlike chain. It's more direct and you can understand it better. Semi-flexible means there's some flexibility but not a lot. And this usually applies to the polymer with persistence length is much larger than 1, but also slightly below than raw-like polymer like DNA. So if you have LP between, say, 1 to 100, that falls into the range of the wormlike chain model. Okay? In the textbook, go through and read it. You will find a lot of interesting discussion about all these polymers. We need this new model, and indeed. And I want to go into 2 details, but Karaki-Pratt wormlike chain model is a very good way for you to understand how does a chain persistence length impact end-to-end distance. So this model is something so different with other model, and you should not able to apply what we used in free joint chain, free rotation chain model. It basically uses 2 parts. I can, again, if you want to know the math part about that, I'm happy to go through that. But it goes through something called Taylor expansion, so which is a way shown in Tim Lodge's textbook, how you can expand a parameter, use the exponent to expand it, and using some simple simplification, you can convert the equation what we know in the end-to-end distance r squared to what we have shown here using the first approximation. So what's the first term? Let's first look at. This is actually NL squared. Why? Let me show you why this is the first term is 2LC multiplied by LP would be equals to NL squared. The reason is LCE is actually equals to NL. This is the contour length what we have discussed. The contour length will be number of bonds in each bond length. And LP is equals to 2 divided by C infinity L. And now if you apply those two terms in there, you would see this will be, sorry, I missed C infinity here. So this would be equals to C infinity NL squared. Okay? So this is exactly the definition for all the model we have discussed in free rotation chain model and hindered rotation chain model. The second term is due to these rigidity factor, what you need to consider in L contour length and persistence length. But I want to leave that as homework. You can understand in two extremes. If you have the extreme that your contour length is much bigger than LP, contour length is much bigger than LP, that means your chain is very flexible, right? Your contour length, how long your length is, versus LP, your persistence. That you can simplify this into what we have discussed, into only leave the first term. So this term will diminish. And I want to leave that for you to practice that as homework. In the other extreme, if your LC is much smaller than LP, this is basically equivalent to very rod-like chain. You can describe the end-to-end distance will be equals to basically LC squared, okay? We already discussed several of these chain models, how their persistence length would be. We can read it one more time. You have cellulose, which is some sort of semi-rigid line, to polyphenylene. This is a conjugated polymer. You can see LP is about 13 nanometer. And you have other semiconducting polymer. But something useful is for DNA. This is about 60 nanometer, as you can see. What is so useful about the generalized equation shown here is this can describe two limits. You can describe both the coil-like and rod-like polymer. And okay, so what this term is showing is how the end-to-end distance will be related to L divided LP. So if it's a rod-like term, your end-to-end distance H squared will increase much rapidly because, as we have discussed, end-to-end distance for rod-like polymer would be R squared would be equals to end-to-end distance, basically NL squared. So it will be equals to NL L squared, right? So in the coil state, in the Gaussian coil, end-to-end distance will be proportional to C infinity NL squared. So this will be differs by a factor of n, right? Because C infinity is constant, so it's not important anymore, but this term, n, will be different. That means end-to-end distance in one case would increase by a power of factor of 2 in the case of the rod-like compared to coil-like, the slope, or in the increase rate for end-to-end distance will be only to the power of 1 to the length or degree of permutation. Okay. This model has been shown to be more broadly applicable with polymer with very bulky side chains, conjugated polymer, liquid crystalline polymer, and other oligomers, because they are more, you need to consider more like wormlike chain model than these flexible chains. So this is sort of the practical explanation. I'll leave it here as a homework, but the answer is already here. Please go back and try to review what we have discussed in this equation, and we can go through the equation if you have a problem. Okay? With that, we can summarize today's lecture. And I think a few words to summarize today's work is a rigidity of the polymer is very important parameter, so you have to know how to get that, and this will be a suitable parameter to discuss how rigid your polymer chains. Don't use end-to-end distance, that's not a reliable parameter. And you need to know the concept about what is persistence length, what is Coulomb length, as well as how this will be linked to what we have talked about as characteristic ratio. So in the next class, we're going to discuss how we can physically measure end-to-end distance. Up to now, we only talked model how we can measure, how we can visualize them, but they're actually a good technical technique can use to measure it. And the technical technique is called scattering technique. I won't teach about that technique, but Professor Yung Simon will discuss it with everybody. And his lecture in chapter 7 will talk about light scattering and other X-ray scattering technique would be able to measure. And what it is able to measure is something called radius of gyration. It's not end-to-end distance, but glad that those two parameters are closely linked. And we will start the next lecture talked about what this radius of gyration is, and we can go from there. So thanks for tuning in, and I'll see you tomorrow on the live QA session. Okay.